Hey everybody, in this video I want to sort of talk about what my first week of homework looks like in my graduate math classes. So this semester I'm taking uh, graduate classes in algebra analysis and topology. They're all sort of like the first intro level. Um, so I'm just gonna sort of go through our like first homework assignments. So here, this is the algebra homework. Um, and so, we're starting with group theory. So these are pretty like um, just sort of basic group theory questions. Um, he gave us a bunch. You can see there's 7 here, and then I think like 9 he chose from the book Algebra or Abstract Algebra, I forget the title, by Dummett and Foote, which is a commonly used book for graduate level algebra classes. Um, However, we only had to do the ones that are starred. So there's this one that was starred. I'm not going to show that one because I don't have the book pulled up. There's these 2 that were starred. And then 4, 5, and 6. Right. So it was only, kind of a 5 problem homework. Um, so I'm just gonna walk through. I'm not gonna give full proofs because there's 2 other homework assignments, but I'm just gonna walk through this. So here we have a problem about finite cancellation semigroups, or just, yeah, well, kind of just cancellation semigroups, I guess. B deals with finite and C deals with infinite. So a semigroup is um, just a set with a associative binary operation, which means you have some function which takes 2 elements in your set, spits out another element in the set, and associative just means if you are applying the operation when you have 3 elements, it doesn't matter if you do sort of like the first 2 and then the third, or if you do the second and third and then the first. So not like order matters, like how you might have a group operation where it might not be commutative, right? So commutative is when you're dealing with actual order. Associativity just means um, sort of the order in which you apply the operation. Um, and so it's a cancellation semigroup if um, you can cancel out sort of this like sort of elements of a set um, being on the left or right hand side of an equation. So here we have left cancellation, here we have right cancellation. Okay. So part B says, show that a finite cancellation semigroup is a group. So the basically the way you do this is you say S is, some finite set. That's a semigroup. And I'm just gonna, sort of denote the operation by usual just like XY multiplication. Um, and the first thing to getting that it's a group, right? So a group is a semigroup with an identity element, and everything has inverses. Now, inverses rely on the identity existing. So the first step, so step 1 is find the identity, which typically you denote by E. And one way you can do this is by noticing that if you multiply the whole set by some element, x sub I, then because of the cancellation property, this is actually a permutation of the set. And in particular, there's going to be some x sub k such that x sub k xi equals xi. And then basically x sub k here, well, really you would do this first for like x1. So you would define k based on 1, and then you basically prove that x sub k is your identity. And then once you prove that it's an identity, you show that everything has an inverse, which basically just holds from this permutation fact. And then that it's also unique also follows from the permutation fact. And then for an example of an infinite cancellation semigroup, which is not a group, I said the integers mod, not mod, the integers removing 0. So in other words, you know, you have -3, -2, -1, and then 1, 2, 3. And then with the operation being, let me think, multiplication, under multiplication. So you have cancellation because you know, if ax equals ay and these are all non-zero integers, then you know we can pass up to the rational numbers and then sort of divide by a, basically because the integers have no zero divisors, which is, you know, an algebra term for rings. But since you don't have 0, well, sorry, but so you have an identity actually. So this is a bit stronger than a cancellation semigroup. It's a cancellation semigroup with identity, but you don't have inverses, right? For instance, there's no integer such that 2x equals 1. So this isn't a group, but it is a semigroup because multiplication of integers is associative. And it is a cancellation semigroup because you can always, because essentially the integers have no zero divisors. Okay, so that's question 2. And then I guess I'm not really gonna go through all of these just because there's other assignments I want to get to. So this one's interesting, part A, which says that if a group G has even order, which means there's an even amount of elements, then the number of elements of order 2, which means x is not the identity, but x squared is. That's what the order 2 means. The number of such x values is odd, and therefore there has to be at least one. Since 0 is even, right, there can't be 0 of them. So for any group of even order, there is, you know, some element of order 2, which is kind of fascinating. And the proof of this uses essentially the idea that if x squared equals e, this is the same thing as saying that x is equal to its own inverse. Okay. So basically, the elements that don't have order more than 2, they are not equal to their own inverse. And so those elements of order greater than 2 have, or they come in pairs. X and X inverse, right? Because these are going to be different elements. But the elements that are their own inverse, um, they don't get paired like this, right? Because, well, they get paired with themselves. So essentially, if you write out, you start with the identity because the identity is its own inverse. And then you have the elements of order 2. And then you have the elements of order greater than 2. Well, these come in pairs, so there's an even amount of these. Now we know there's an even amount of group elements in total, and so that means that there's an even amount of elements who are their own inverse. But since E is among these, and E is order 1, technically, that means that the number of elements of order 2 is 1 less than an even, which means it's odd. Okay. And then part B is saying that the statement about G being abelian is equivalent to these maps iota and H being homomorphisms, namely the inverse map and the square map being homomorphisms. And this is because, for instance, the inverse map being a homomorphism means that B inverse A inverse equals A inverse B inverse. And then the square map means that AB is equal to A squared B squared. And then you can sort of cancel out the A and the B, and so you get BA equals AB. Okay. And then these two I'm not going to go into, but this one is about the order of a product of commuting elements and sort of certain conditions, and then finding a counterexample where these things fail if they don't commute. And then 6 showcases two matrix groups, and we're sort of studying how they relate to each other and the cosets that they form. Okay. So now we're going to switch over to analysis. Okay, so now we're at the analysis homework. So my analysis class, a graduate analysis class, usually starts with measure theory. So the typical graduate analysis class is sometimes called measure and integration. So in undergrad, your analysis class is like defining the real numbers and studying the topology of the real numbers and Riemann integrals and stuff like that. But for graduate analysis, you instead take a more abstract approach. You assume that you already know how real numbers work, and a lot of stuff, you also use a lot of topology. So you're already assuming you have real numbers and topology sort of defined. And then you extend that idea and you look at sort of measurability, and then you define measures, and then you can define integrals based on measures. So here in number 1, we're looking at the Boral sigma algebras of certain generating, basically certain sets that generate the Boral sigma algebra of the real numbers. So this is a lot of terminology. I don't have any videos on this. I know Phematica does. Of course, you could just Google, but I know Phematica has some video on measure theories. The term Boral means that the sigma algebra is generated by a topology. And a sigma algebra is a collection of subsets. So it's kind of like a topology, right? A topology is a collection of subsets. Sigma algebra is also a collection of subsets that is closed under complements and countable unions. The two things put together, since you have complements, this also means it's closed under countable intersections, but obviously for defining it, you only need either unions or intersections, right? So this BR is the Boral sigma algebra of the real numbers, meaning that you start with the topology of the real numbers, i.e. just the set of all open sets, and then you extend it to contain both complements and countable unions. Well, you already have arbitrary unions in the topology, but you can't have sort of arbitrary union. Arbitrary means you could have an uncountable union, but you don't deal with uncountable unions with sigma algebras. Okay. Now these B4 and B8, these are specific sets of sort of generators for the Boral sigma algebra. So if I remember correctly, I think B4 consists of the closed intervals AB, and then I think B8 might be like the closed rays that point rightwards. The idea is that sort of you take some collection of sets that look nice and then they generate the same Boral sigma algebra. So like B1 consists of all the open intervals, right? So you have basically a bunch of different types of intervals, and these are going to give you the same thing in the end. So that's what this first one does, is asking. All right. For 2, 2 deals with sequences of subsets and dealing with sort of limits of these. So this is the lim inf, or the limit infimum, and this is the lim sup, or limit supremum. And you can define these for sequences of, like real numbers also. But here we're dealing with sequences of sets, which kind of work in a interesting way. So the way these are defined, the lim inf of E sub n is, I think, the union, as n goes from 1 to infinity, of the intersection of k greater than or equal to n of E sub k. So, in other words, it's the union of all the intersections of sort of the sets past a certain index. So if x is in the lim inf of E sub n, then x is in some union, which means x is in one of these intersections for some n. Meaning that x is in E sub n plus 1, and so on, right? X is in all the E sub k values past E sub n. The lim sup is defined similarly, with just flipping the union and intersection. So here this is the intersection of all the unions. All the unions past a certain point. And so the goal here is to show that there are subsets. The lim_inf is a subset of the lim_sup, which is pretty much just it's just a set theory argument. Then B, well, there's a typo. B says give an example where the lim_inf is empty and the lim_sup is the entire set. So I'm assuming that, you know, that my teacher kind of makes a lot of typos. And for this, I said the alternating sequence, you know, I guess I shouldn't use curly brackets. I don't know what to use here. But just alternating empty set and the whole set. And the reason this works is because these intersections here are always going to be empty because you're always going to have an empty set in the intersection. So then you're unioning a bunch of empty sets, so that's just going to be empty. And then here, your union is always going to be x because you'll always have an x term in your union. So you're intersecting a bunch of x's, and so that's going to give you x. Okay, so this is kind of like a trivial example. Okay. Now, I'm not going to talk about 4, but I'll talk about 3. So here we talk about functions being measurable. So first, what does it mean for a set to be measurable? Well, a measurable set is just an element of a sigma algebra. That's all it is. So a measurable set is an element of a sigma algebra, which again, a sigma algebra is a collection of subsets on, you know, X. Oh, and here R in R bar denotes sort of R adjoin minus infinity, infinity. So this is called the extended real line. It's a two-point compactification. And we deal with R bar because when we get to measures, which are functions, which you know, kind of give a size of a set, you could have, for instance, the measure of a size being infinity. We want infinity to sort of be like a number that we can deal with. And so that's the idea of the extended real line. So yeah, measurable sets are just elements of the sigma algebra. So here, when we have f and g being functions from x to r bar, we're kind of assuming that x has its own sigma algebra and r bar has its own sigma algebra, which is typically assumed to be the Boral sigma algebra or even the Lebesgue sigma algebra. But we haven't kind of gotten to that yet. So yeah, so that's what a measurable set is, and then a function is measurable if f inverse of b is measurable for all subsets of y, for all measurable subsets of y. In other words, if I take any element in the sigma algebra for y, then the inverse image of that set has to be in the sigma algebra for x. So this is very, very analogous to f being continuous, right? For f being continuous in topology is the inverse image of open sets are open. And so here the inverse image of measurable sets are measurable. And in fact, this is such a connection. Remember that the Boral sigma algebra is generated by a topology. Well, in a Boral sigma algebra, any continuous function is measurable. So in Boral sigma algebra, continuous functions are measurable. Okay, so that's the terminology here. So I've kind of written all over the problem, but we're basically just asked to show that given two measurable functions, the set of points where they are equal is measurable. And the way you can show this is the set of measurable functions here, the set of measurable functions forms a vector space. So in particular, I'm going to kind of write down here, f minus g is measurable. So, so this set x where f of x equals g of x is the same thing as the inverse image of 0 under the map f minus g. Now f minus g is measurable and the set containing 0 is measurable. So this is measurable. So this is the inverse image of a measurable set under a measurable function. So this is measurable. Okay, so that's the analysis homework. And then there's 4, but I'm not going to talk about that. So now for topology. Wait, did that not pause? Okay, that didn't pause. Okay, one sec. Okay, I'm back. So here's the topology homework. Just 4 questions, and they're all pretty straightforward point set topology questions. So for 1, we show that for functions from R to R, the epsilon definition, the epsilon delta definition of continuity is equivalent to the topological definition, right? So remember, epsilon delta is that, so if x is an R and epsilon is greater than 0, then f is continuous at x if there is some, basically given any given any epsilon greater than 0, there's some corresponding delta value such that basically y, or x minus y is less than delta implies that the absolute value of f of x minus f of y is less than epsilon. So in other words, I can always find some delta such that whenever I have a value y which is within delta of x, so this is equivalent to saying y is in the interval x minus delta to x plus delta, then f of y is in f of x minus epsilon to f of x plus epsilon. So points that are close to x are going to are going to have images which are close to f of x with arbitrary precision. And of course, the topological definition is that inverse images of open sets are open, and since you actually only have to check that for basis elements. So the basis for the topology on R is the open intervals. So you only have to check open intervals, and then that becomes pretty easy. Okay, so that's one. Two has to do with the subspace topology. If A is closed in Y and Y is closed in X, then A is closed in X. So so here Y is a subset of some topological space. So this has a topology. Then the subspace topology, which I talk about in my series on topology, on Y is the set of U intersect Y, where U is open in X. So I take my topology on X, right? So all the open sets, and then I just intersect them with Y, and that's my topology on Y. Okay. So in other words, A is open in Y means that A equals U intersect Y for U open in X. And you can prove sort of the same thing works for closed sets. If A is closed in Y, then A is equal to C intersect Y for C closed in X. So here, if A is closed in Y, then I know A equals C intersect Y, where C is closed in X, and we know Y is closed in X. The intersection of two closed sets is closed, so that shows that A is closed. So the only kind of non-trivial part of this would be showing this, but we actually showed that in class, so I didn't have to write that down in the homework. All right, number 3 has to do with relating the condition of being Hausdorff to the condition of a diagonal in the product topology being closed. So for some rehash of definitions, Hausdorff means that if P and Q are in X and they're not equal to each other, so they're distinct points in X, then there are disjoint open sets UV such that P is in U and Q is in V. So the typical image you want to think about is like in a metric space. So like let's say R2. If you have like P and Q, say like this. In a metric space, you have balls that are centered around a point, right? So the set of X such that the distance between X and P is less than epsilon. Then if P and Q are distinct, the distance between them is greater than 0. And so you can use that distance to define your epsilon values and construct open balls around each point. They're going to be disjoint if the epsilon is small enough. And so you see that metric spaces are Hausdorff. That's usually like the typical picture to have in mind. Okay. Now the diagonal let's again use sort of the example of R2, right? So R2 is literally just the Cartesian product of R and R. And so you have a topology on R2 given by the product or box topology on R times R. Now, product and box topologies are they're two different words technically in topology, um, but when you are only dealing with a finite product of sets, so like here we're just dealing with one set times another, um, they coincide. But when you have an infinite amount, the definitions kind of diverge from each other. But anyway, we have a basis for the product topology is U times V with U and V open. And you can actually further reduce this, I believe, to even just U and V being basis elements. So for instance, with R, your basis elements are open intervals. So the product of two open intervals is going to be sort of like an open rectangle, which kind of motivates the term box topology. So the diagonal, right, is just the set of points in x times x where both entries are equal to each other. So in R2, right, that just looks like this line, right? The set of points x comma x. And so the problem is to show that if that the diagonal is closed if and only if x is Hausdorff. And the idea is that if you have some point outside the diagonal and you have sort of some open set which is around the point. So first of all, if you have a point P in xx, or x times x, that's not in the diagonal, then that means P is represented by coordinates P comma Q, and P is not equal to Q, right? Because it's not on the diagonal. Right? And so this open set, you can take it to be sort of a basis element. So the basis element is going to be like this box. And this box gives you open intervals around P and Q. So here this is Q and this is P. And then you have open intervals. And these are actually disjoint because if U intersect V was not empty, right? So X was some element of U intersect V, then X would be an element, or sorry, X comma X would be an element of U times V, because X would be in U and X would be in V, so XX would be in U times V. But we're saying that U times V is contained sort of outside of the diagonal, right? So because of that, you can't have U and V being intersecting. So that's why this condition is equivalent to being Hausdorff, which is kind of cool. Finally, 4 is to show that a subspace of a Hausdorff space is Hausdorff, and that's pretty straightforward. You take your points in Y, and then, of course, since Y is a subset of X, then P and Q are points of X, So you have disjoint open sets U and V containing P and Q, and then you just sort of go down a step to Y, right? You do U intersect Y and V intersect Y. These are open in Y by definition. They're also disjoint because U and V are disjoint, and they also contain P, and well, this one contains P and this one contains Q, because P is in Y by definition, and P is in U because U was chosen to contain P. Similarly, V contains Q. So yeah, that one's pretty simple. So yeah, I hope this video is interesting to someone. Just wanted to show you what graduate level homework is like. At least this is sort of like first semester stuff at not really like a big university for math. Like it's not like MIT or anything. They probably have more intense homework. But yeah, I just wanted to kind of show this off. So hopefully you enjoyed it. Hope you watch some other videos.